In this video, I'm going to show you how to derive the tree-level differential scattering cross-section for pair creation in a nuclear electric field as described by scalar quantum electrodynamics. It's a cool calculation, and it's a beautiful result. I've done the standard QED version of this calculation already, and now I'm going to show you how it goes in scalar QED. Scalar quantum electrodynamics given by this Lagrangian is the scalar generalization of standard quantum electrodynamics. If you are unfamiliar with how this theory is constructed and quantized, I recommend you to my An Introduction to Scalar QED video. There's a link to that in the description. This derivation is extremely short because I have already done most of the work in previous videos. Specifically, this calculation is very similar to three others I have already done: Bremsstrahlung in scalar QED, standard QED pair creation, and the Bethe-Heitler formula derivation. Links to all of those in the description as well. Because of that similarity, the math done in those videos can be repurposed to make this derivation really quick. In my An Introduction to Scalar QED video, I introduced the standard scalar QED Feynman rules, which are these. Additionally, in my videos on deriving the Bethe-Heitler formula and the standard QED pair creation in a nuclear electric field differential scattering cross-section, I obtained the Feynman rule for a Coulombic virtual photon. This is important because that Feynman rule is beyond the standard set. I then discussed its use in scalar QED in my video on deriving the scalar QED version of the differential scattering cross-section for Bremsstrahlung in a nuclear electric field. The Coulombic virtual photon Feynman rule that I revealed in those two videos is this: considering the two different kinds of vertex functions given in the table of Feynman rules, standard ideas yield the following list of Feynman diagrams for the complete tree-level contribution to the reaction of interest. Energy and momentum conservation naturally must work the same as in the Bremsstrahlung scalar QED problem that I already did in a previous video, because the only difference between the Feynman diagram / amplitude is the interchange of a pair of external lines, which naturally changes nothing about the math that controls how energy and momentum conservation appears in the problem. I therefore refer you to the discussion of energy and momentum conservation in that video to see how these results come about. All of these relations are only very slightly different because of the interchange of particles, and they come about via the same process. With the Feynman diagrams, the Feynman rules, and the energy and momentum conservation relations sorted out, we have everything we need to write out and simplify the Feynman amplitude. Directly using the Feynman rules yields this Feynman amplitude. We can then start simplifying with energy and momentum conservation and transversality. Transversality gets rid of this term and also k's that show up here after we apply momentum and energy conservation. We can also combine like terms and rearrange things a little bit, and we get down to here. We can then simplify the denominators quite easily, which gets us to these. Inserting that gives us a very simplified answer. This is way smaller than what we started with, which is definitely convenient. As mentioned previously, we have the usual problem with scattering cross-section calculations involving a Coulomb field. The usual differential scattering cross-section general formula doesn't work here because one of the incoming particles is virtual. I showed how to solve this problem in my Bethe-Heitler formula video and in my standard QED pair creation video. In fact, the only thing that one must change in the exact math given in my standard QED pair creation video to get what applies here is the standard normalization of the massive particle states. Specifically, we must change it from fermionic to bosonic. Making those tiny changes produces this result. We want the unpolarized differential scattering cross-section. We therefore must do the appropriate spin summing and averaging. We must average over the spin of the incoming particles and sum over the outgoing particle spins. Only the incoming particle has spin in this case, so we just average over the incoming particle. That gives us this. The standard nuclear electric field pair creation result is with respect to the two outgoing solid angles and the antiparticle energy. Therefore, we must change to spherical coordinates in momentum 3 space, which gets us to here, and that reveals those desired solid angles and the magnitude differential we want. And we must integrate over the scalar particle momentum magnitude. We must remember to handle the delta function properly when doing this integration. For a detailed treatment of this process, I again refer you to my Bethe-Heitler formula derivation video or my standard QED pair creation calculation, which is the direct analog of this. Doing the integration produces the following result here. Inserting this quantity, which we calculated over there, yields this result. We can then rewrite the antiparticle energy differential in terms of this differential here, and we see we get this result, and we have the factors we need already present in order to make it show up exactly. That leaves us with this result. So now we have the general differential scattering cross-section formula, and we already calculated and simplified the Feynman amplitude, so all we need to do is insert that. Inserting that gives us this. We can then pick a parameterization, and I picked the standard parameterization parameterization for this problem, which is the same parameterization used in the standard QED analog of this problem, so you're already familiar with it if you've been watching my quantum field theory lecture series. Now, I've written out the description of what all the parameters mean here in this video as well, although exactly that description was in my standard QED version of this calculation. If you want to read it here, you can pause the video, but I'm just going to move on. Inserting that parameterization gives us this result directly, and then a tiny bit of simplification yields our final answer, and isn't it beautiful? So now you know how to derive the tree-level differential scattering cross-section for pair creation in a nuclear electric field as described by scalar quantum electrodynamics. I hope you found this interesting and fun. If you did, please give it a thumbs up and consider subscribing.